under root 6. So now we have xm and this thing x1 and x2. Okay, so now we can write the equation for it. So v1 would be equal to I1 into, this is I1 into 2j plus I2 in the same inductor. We are having another voltage being produced, which is the mutually induced. So mutual is from this circuit. So from I2 we are getting how much communication? We are getting a j omega under root 6 communication. So this is our V1. Now similarly V2 would be equal to, first write it for this I2. So I2 is flowing through this 3j. So I2 into 3j is the first part, whereas I1 into j omega under root 6, which is the mutual inductance, and coming from I1. So this is our V2. So this is how we use these terminologies. Now the next thing that we should worry about is the flux direction, whether the flux direction is supporting the current's direction or not. So for that we use this dot notation. We'll talk about this dot notation later in the same circuit chapter, but let's have a brief idea about it. If two currents are present in a circuit, and let's say there are two dots in it, and both the currents are going towards the inductor from the dot side, so input to the circuit and input to the circuit, we will use a positive sign here. But if one dot has a current entering and other dot has a current outgoing from this circuit, from this inductor, then we will write a negative sign here. So this shows the communication of two inductances with one another, that how the flux is interacting. Sometimes the flux might be in reverse order. Let's say this current is not here, this current is here. So this current will totally oppose this one. So in that case we should subtract from it. So this is a brief introduction to dot notation. Later we will study it. Okay. So this is the dot convention. In dot convention we say that the current's direction is in our hand. Current's direction is in our hand. So if we say that one current is like this and other current is like this, so both currents are entering the circuit, so we will write a plus sign with both the mutual inductances. So plus is here, plus all around. But if the dot is used like such, then in this case this dot is on the outgoing side, so the outgoing side will give us a negative sign with m. So in this case, if we write the equation, what would we write for the same problem? We will write V1 is equal to I1 into 2j minus j omega under root 6 into I2. Similarly, V2 is equal to I2 into 3j. I am using I2 directly here. This should be here, but I am using it on this place. And minus j omega under root 6 into I1. So j under root 6 is our m and j omega m, and I1 is from current. So this is from current, this is M12, this is M21. Okay, so I hope you got the idea. So there were two cases. In the first case we had a positive sign. So here if we write the equation, this would be V1 is equal to I1 into d by dt I1 into L1 and plus d by dt of I2 into M12, or V2 would be d by dt of I2 into L2 plus d by dt of I1 into M21 in 2 due to 1 and 1 due to 2. Okay, so this is positive. Now if here we consider it, we will write V1 is equal to d by dt of I1 into L1, and since it is entering and it is leaving, minus d by dt I2 into M12. Similarly, V2 is d by dt of I2 L2 minus d by dt I1 M21. So plus is changed to minus if this is entering, leaving. Similar case would happen if we had something like this. Not here. So something like this. So here it would be leaving current and here it would be entering current. So red is the new scenario for us. So in that case we will also use this negative sign. Now this is assuming that we are having n number of fluxes. So in n number of fluxes, the first one would be the in and the second one would be from. So in L1 due to L2 would be M12. So here we would use d by dt of I2, and this would be inside the V1 due to current in 2. Similarly, we can write V is equal to V11 plus V12. So V11 would be d by dt I1 and L1. So self are similar, mutual are different. So this is the summary. Okay. Now we are having this explanation of the previous dot base convention. So this is now pretty much easier. We are having M instead of L12 or L21. So we were going already ahead of this discussion, this book's discussion. Let's examine it. This first current is like this, second current is like this. We are having positive entry, positive entry. So if we write V1, so V1 would be equal to V11 plus V12, whereas V11 is d by dt I1 into L1 and V12 is d by dt from I2 in L1, so that would be termed as M, because we have said that L12 is equal to L21 is equal to M, so we are using M. So this is the case, but if we replace this dot over here just like this, so now it is here, so we can still say that this is leaving and this is leaving. So in both cases this thing is leaving. So if we write the V1's equation, this V1 is up minus as well. Okay, so this is plus, this is minus. So we can write it as minus V1 is equal to, so leaving and leaving, so d by dt I1 L1 plus, because both are leaving, so we will write plus d by dt I2 M. So this minus, if we make it to go here and here, so we will get minus and minus here. So same equation holds for our type of logical explanation of the dot. Solve this second side by yourself. I will just give you a clue. V2 is equal to V22 plus V21 in 2 due to 1 in 2 due to 2. So let me solve this side for you. Here we will have d by dt I1 M. So d by dt I1 M is here. Solve this one by yourself. Okay, so this is a learning example in which this M is not given, I guess. Nothing is given, L1, L2 or all the things are not given, and we are to solve this thing by this mesh equation analysis based solution. I guess this is a bit harder example, but let's have some idea of it. So we are having two loops. This is our loop 1 in which the current's direction is like this. This is our loop 2 in which the current direction is so we can assume current direction from our on to make our circuits easier to solve. So let's solve it. So let's just not go into these details, just let's write our own equation for it. So I am creating another empty slide and then solving this circuit in our way. Okay, so the circuit was something like this. We had a source here and one resistance and one inductor and another inductor and a resistor in here and a dot here, a dot here. Current I1 is this and I2 is this, and this is R2, L2, L1 and R1, and this is V. So let's solve it. V would be equal to I1, this current in loop 1. Let me write it by some other color. So I1 into the resistance in this whole path. So what's the resistance in this whole path? We had studied the KVL in our previous lectures. So let's write that thing. So we will have R1 plus j omega L1 plus j omega L2. So this is our V11, the voltage of self-induced current. So V11 is I1 into R1 plus j omega L1 plus j omega L2. Now it's time to check the mutual inductance. So that would be V12. So here if we check the current is entering this dot and the current is entering this dot. So both currents are entering. So we can write it as plus I2, and now the mutual inductance can be calculated by j omega and under root L1 L2, which is our mutual inductance. So we can write it as j omega m. So this is the equation for our first circuit. Now we see that in the first circuit we are having this I1 passing through this inductor as well. So I1 is not only causing this induced EMF in this, due to this I2 is causing in it, and I1 is also causing in it. So if we check this I1 in it, this I1 is leaving with respect to this I1. So we can write it as minus I1 j omega m, because here if we check the total current in this inductor, the total current is I1 minus I2. So we should be checking this thing as well. Okay, now if we write the equation for this second, now if we check the second inductor, so in second inductor there is only one inducing current. That current is this I1. So let's add that one to it. In second inductor the I1 minus I2 is leaving, so we do not want to indulge into I1 minus I2 or I2 into I1. The I1 is leaving in it, and that leaving current is entering in this one. So we can write it as minus I1 j omega m. So m is mutual inductance and it is caused in 2 due to 1. So we are using the current of 1. So this is how we will add up these two inductances. So if we check the previous slide in it, so V1 is equal to R1 I1 LDI1 and L2 I1 minus I2. So here if we see there is one thing missing, and that thing is the self-inductance that is being dropped in this L2. So L2 is here, and in this L2 I2 is going, so minus I2 j omega L2, the self-inductance of L2 is also should be here. So we are having this R1 I1 L1 D1 and then L2 I1 and L2 I2. So L2 I1 was added to this one in our method as I1 into R plus j omega L1 plus j omega L2, and then this I2 was written separately as minus I2 into j omega L2, and after that mutual inductance in this due to currents in this. So there were two currents in it, I2 minus I1, so I2 minus I1 was written in here, and then the mutual inductance in 2 due to 1 was written in here. So we had 1, 2, 3, 4, 5, 6, 7, 8 terms. So let's check it. 1, 2, 3, 4, 5, 6, 7. Sorry, let me check it again. It would be 7 terms. 1, 2, 3, 4, 5, 6, 7. 7 terms in here and in here. So we are good to go. Now this was, as I told, this was a bit complex. So you should just have, you might had an idea of how we will calculate this mutual inductance. Let's calculate the second loop's equation for it. So in second loop there is no rises, so 0 would be equal to now, let me write it in some other color. So 0 is equal to, now I2 is our positive current, so I2 R1 plus j omega L2 is here, and another voltage will drop in this one due to current in 1, so minus I1 into j omega L2. So this is the self-inductances. Now talking about mutual inductance, so in I2 there the current is I2 minus I1, so we can write it as I2 is entering, so I2 minus I1 into d by dt of m. So not I2 minus I1, we will write I1 here because there is voltage produced in 2 due to 1, so we are using this one, so things have become easier. So the 2's equation is something like this. So now if we check this thing, so this is same as ours, R2 I2 and L2 I2 minus I1 and M I1. So there is M di1 by dt, and we had this M and d of I1 by dt. Okay, so this was this one. Okay, and similarly I2R and I2 d by dt I2 and L2. So I2R and d by dt I2 this, and d by dt L2 I1, this is d by dt L2 and I1. So our method is a bit easier than this one, so just use this method. Okay, this was a hard example. Let me tell you again, our examples that we should study should be a bit easier than this one. Okay, now more about this dot convention. Let's just call our dot convention. If current is entering and current is entering, we will have positive signs with M. If current is entering and current is entering, but this sign is negative, so I don't know what this problem is trying to say. Let's just make it positive. Okay, then we would have a positive with it. If it is entering and it is leaving, then it would be negative sign. So this is the dot convention. Use your own direction of current, and always choose a direction in which this source and this current has same direction, so you will not have to write these minus signs with it. Okay, this is another explanation of this V1 and V2. In this explanation, we convert this example to our base case. So we had I1 in this direction, but now it is in this direction. I2 was in this direction, but now it is in this direction, because this thing is reversed. So due to this reverse phenomena, since our voltage is reversed, so we are writing minus with it. So we are using the same base phenomena, but we are trying to use our previous equation for this new system. So system is to be compared with the previous one. So previous one was V1 L1 d by dt and V2 Mi2 by dt. So here the current is in opposite direction, so we are using minus sign with it and minus sign with it. So there is nothing special about it. You just have to use loops, and this whole thing will turn out easier. Now here is another learning example. We are having two coils and we want to connect it with different scenarios. In the first case, we are directly connecting it and assuming that these dots are having the input current. So here this current goes like this. So we will have a positive sign with N. But if we had some connection like this one, so in this case the current is this. So what are we doing? The current is leaving this second node and entering this first node. Okay, so we will have a minus sign with it. So this must be generalized. For a leaving or entering, it should be negative, and for entering or leaving, it should be positive. Okay, so this is it for this circuit. So now you can easily solve circuits with these example problems. Okay, so you just go through it and let me know whatever is necessary. We will solve some easy and then some moderate and some hard example in our next lecture. So till then, bye. Thank you.